Those who are here over the summer, a lot of this is going to be some recap, but my project is dynamic RNA. It's an attempt to simulate or create a new algorithm for doing molecular simulation, specifically polymers such as RNA, DNA, or proteins. So before I get into the specifics of what I'm doing, we sort of have to know what I'm trying to do. So RNA, or ribonucleic acid, is one of the fundamental chemicals for life. It allows cells to take information encoded in DNA and turn that into useful things like proteins, enzymes, stuff like that. So RNA is made up of 4 basic molecules. Each one is a monophosphate attached to a base. So there's adenosine, cytosine, guanosine, and uridine instead of thymine, which is in DNA. That's the only difference between the two. So I'm trying to simulate this because there's a lot of very useful biological information that can be taken from understanding how the molecule folds, how it, certain physical properties of it that you can't really find experimentally. It's much more easy to sort of predict the properties and understand its chemical reactivity by simulating it, instead of just trying to physically isolate the molecules and then do tests on that. And so the reason why I'm working on this project, the reason why I'm working on this project is because currently there's a bunch of different ways of simulating RNA, but this project really started with a professor of mine, Mohammed Persina. What he did, he developed a dynamic coarsening algorithm, which pretty much, let me go back. So the RNA is made up of 3 basic groups. You have the phosphate molecule, a ribose sugar molecule, and then your base. And so each of these individual groups can be sort of considered a static, solid, rigid body. And so instead of simulating each individual atom and its electron and trying to do all the force calculations based on that, you can simplify it greatly by just making each individual thing a rigid body and defining the connectors as just rotating connections. And that will greatly reduce the computational complexity. But you can further reduce the computational complexity if you were to lock some of those degrees of freedom dynamically. So when there isn't a whole lot of movement between 2 connected parts, you can assume that it's not really moving that much and you can just lock it, take away its degree of freedom, and that way make 2 bodies one rigid body. But if there is a great force or a lot of stress on that joint, then you can unlock it and then give it the degree of freedom it needs to move around. And so this algorithm that Mohammed Persina produced, he needs to have it pretty much validated. We need to make sure that the tolerances, the limit on when you're going to lock, when you're going to unlock, is actually accurate. It'll actually provide useful data. So that's what I've been tasked with doing, trying to develop a truth model where it's no coarsening is occurring, where it's completely fully atomistic, in the hopes that when it's run to completion, we'll be able to see what the model should actually be showing, and that way we can refine the algorithm. So the way I'm doing it, I'm using 3 primary tool sets from the SimTK group. SimTK is a group that has a whole variety of different tool sets for doing rigid body simulation, doing musculoskeletal simulations, all sorts of different projects. It's all on the website simtk.org. So the 3 primary libraries I'm using is SimBody, MoleModel, OpenM, and OpenMM. SimBody is the basic rigid body dynamic toolkit. It allows you to connect individual rigid bodies, and they can be anything as small as molecules or as big as, trusses in a building, whatever you want, and then simulate their movement. MoleModel is another library that's an add-on. They were originally together, but now they're 2 separate projects that'll pretty much turns everything into a molecular simulation rather than a full body simulation. So it gives the ability to create RNA strands very, very easily, to simulate complex chemical interactions without having to do a whole lot. And then the thing that I've been working on most recently, especially over this semester, is OpenMM. OpenMM is a toolkit that allows you to use OpenGL or OpenCL code to accelerate the simulation. Now, I've successfully made a fully atomistic model, but it would take well over 100 hours of simulation time to get really, really useful data and to complete the simulation. And that's just, I can't do that. I can't commit hardware to that amount of time. So I'm hoping that with using OpenMM, I can run a lot of the simulation on a graphics card, which will be significantly faster than trying to run it on a CPU because of its ability to do floating point calculations a lot faster than on a CPU. So yeah, so I guess I've already gotten to the purpose, so I guess we'll just get right along. So over the summer, I was able to, like I said, create the model. I was able to run some preliminary simulations. So I know the simulator works. I just have to let it go. And when I'll know it's going to be done when the molecule reaches equilibrium, when everything stops moving, when it's no longer pulling in, tugging on itself, it's folded to its final state. And that will take a long time. So the only way to know that is when everything, the entire temperature of the system equalizes. And that I won't reach for many, many hours of sim time, like I said. So I've been spending a lot of time and having actually a lot of difficulty with trying to get all the libraries to work together and play nicely. So I've had to build OpenMM, each individual library actually, from their source code and reconfigure and customize pretty much each library so that they all work together on my hardware. So that's been taking a lot of time, and I've been having to talk to the writers of the libraries to try to get everything to work, but it's finally coming together. So I'm hoping to start getting some real results soon. So for this semester, I'm hoping I can run the simulation to actual completion, get real useful biological data, and be able to start comparing the data that I've gotten from my models with that of the models generated by the coarsening algorithm. So then after I finally can get that verified, then we're going to start really working on making new models that are partially coarsened, fully coarsened, and then getting into the dynamic coarsening. So yeah, so that's my project. Is there any questions? Oh wait, sorry. First, I'd like to thank Professor Krishnamurthy, Shana Sullivan, and Orcus.
Yeah. So are you logging whatever the things that you're encountering, we're linking all those libraries and so on. So if you have difficulties, whatever difficulties you have, you should write it so that, and how you overcome it, so that others, it will be at least be useful to others.
Okay, I'll make sure to update my blog.
Yeah, and especially that will be more useful, maybe more useful than your project itself. So, but that's that.
Okay.
What sort of hardware are you running all these simulations on?
I'm running it on just my tower. I have I can't even remember the statistics on it anymore. I have a 6950 ATI card that I'm planning on doing all the primary simulations on. I have a 6-core processor, I don't know the name of it. Venom 2, that's it. Cool. So
I'm pretty sure there's a GPU instance on Amazon EC2. Might be worthwhile.
Amazon EC2, I don't know what that is.
The Amazon virtual cloud service.
Oh, so to do cloud computing with it?
Yeah.
Okay.
I'm pretty sure they have a service that's high GPU, right?
They do.
They do? Yeah.
That's definitely worth it looking into. I was actually trying to see if I can get this stuff to run on BlueGene, our supercomputer here.
That'd be cool.
That would be cool, but unfortunately that's just above my head, so I don't know, because it's all based on the local hardware, so I have to write hardware-specific code to get that to run, so I don't know how well those stuff will play together with cloud computing. So, but yeah, I'll definitely look into it.
Talk to Carruthers or Barbara Feldman.
Yeah, it's kind of like BlueGene kind of solves a different problem.
Yeah.
It's kind of completely different.
Yeah, it's mostly for heavily multi-threaded problems, which this isn't as good as being multi-threaded. Well, thank you very much.